All right, so last class we covered a bunch of nomenclature stuff primarily. We also talked a little bit about converting between mass and number of moles last class, and we're going to continue on with doing the rest of the math in the chapter. So one thing that we'll often be interested in is the composition of compounds, so how much of a particular element or elements is in a compound. So our chemical formula, in combination with our molar masses of the constituent elements, indicates how many of each element we have, just relative quantities of each element in a compound. This is very helpful information in some circumstances. One of the ways that we can quantify this, put a number to it, is with mass percent composition, or more commonly just mass percent. And a general formula for mass percent is that the percent equals the parts over the whole times 100%. And oftentimes these will be calculated values. We can calculate the part, we can calculate the whole, or we've measured the whole or the part, we can do the maths. So the percentage of each element in a compound can be calculated two different ways. One, if we have the formula, we can calculate it assuming that we have just 1 mole of each, the compound and how much of the particular element that we care about. So the mass of X, where X is any element. How much of that element do we have in 1 mole of the compound, divided by the mass of 1 mole of the compound. The reason that we're using 1 mole, strictly speaking, you don't have to use 1 mole, but the reason we're using 1 mole is that so our molar mass just turns into grams. So molar mass, which is grams over moles, times 1 mole equals grams. So it's the grams of the product in 1 mole, and then on the top, whatever the constituent part is. We'll see some examples of that. So we'll have the subscript of whatever our element is times the molar mass of the element to get that top portion. We can also do an experimental mass analysis. So this is from measurements. We'll be doing something similar to this today. So the mass of X, where X is whatever element we care about, divided by the mass of the compound, and times 100%. And if you were to add up the percentages for all of the different components, sometimes it doesn't total exactly 100%. It might be more, it might be less, just because of the way that rounding ends up working out. So it's completely normal to end up with like 99.8 or 99.9 or 100.4% total, just because of rounding errors, depending on how many things you have. I'll give us some time to frantically write these things down. All right, mass percent composition, starting from acetic acid and its formula. So acetic acid is the active ingredient in vinegar. It has the formula HC2H3O2. We know it's an acid because why? Starts with H. The other way that we could have figured out the snarkier answer, it's got acid in the name. So acetic acid, it's got the H in front, that lets us know that it's an acid. So we want to calculate the mass percent composition of oxygen in the thing that we were given, which is acetic acid. So we need to calculate the molar mass. Find molar mass of oxygen in HC2H3O2. We also need to find the molar mass of the acetic acid itself. So let's start with the molar mass of the whole thing. We've got how many elements? 3 elements. We've got carbon, we've got hydrogen, we've got oxygen. How many carbons do we have? 2. We can find our molar mass on our periodic table. It's the same number as our atomic mass. Right around 12. How many hydrogens do we have? We have 4. We've got 3 in the middle, and we've got 1 in the front. Find our molar mass for hydrogen. It's right around 1. And we've got how many oxygens? 2. And those have about 16 grams per mole each. If we add all this up, this will give us the molar mass. So 2 times 12 and change, plus 4 times 1 and change, plus 2 times just short of 16. The molar mass is 60.052 grams per mole. That's the molar mass of the whole thing. And what would be the mass of just the oxygen in 1 mole of the compound? How many oxygens do we have? We've got 2 oxygens, so we're going to take just this bottom line, this 2 times 15.999. So 31.998 grams of oxygen per mole of HC2H3O2. The other way that we could figure it out, if we wanted to start from this molar mass of 60, we'd take, this is the grams per mole of the total compound, we'd multiply by 1 mole of the total compound, so it just turns into the grams. And then we've got, no, that's wrong. I don't know what my brain's doing. I'm super tired today. So forget what I was saying there. There's another way to get to it from that, but I underslept. So we'll just use these numbers, and this works. So we're going to take the part, divide by the whole, and multiply by 100%. So 31.998 grams per mole divided by 60.052 grams per mole. And since it's a percent, multiply by 100%. So 31.998 divided by our whole thing times by 100. And we get 53.28%-ish. Would actually be 284. That should be correct for significant figures. Questions? Cool. We can also use mass percent as a conversion factor. So we can use it to convert between the mass of the element and the mass of the compound. There's a couple of ways to do this. We can use our mass percent equals grams part over grams whole times 100%. So we can just use this like a formula, rearrange for whatever it is that we're looking to solve for. We can also learn or remember or think about percent. The per means divided by, and cent like pennies, 1 cent. Per 100 is what percent means. So if we make the percentage, the top part in grams, then the bottom part is always going to be 100 grams. Another thing that you can do is convert the percentage to a fraction form. Which is the same as just doing the math, the 69.58 grams of the part divided by the 100 grams of the whole thing. And then this lets us know that for every 1 gram of the whole compound, we have 0.6958 grams of the part. And then use that as a conversion factor. I think for most of us, though, probably using the original formula and just solving it, doing a little bit of algebra, I think that's probably the most surefire way. All right, so we want to know, testing our knowledge, using this new skill, what mass in grams of iron 3 oxide contains 58.7 grams of iron. Iron 3 oxide is 69.94% iron by mass. What is some information that we are given? We're given the percent mass. We're also given the grams of iron. What are we finding? What are we finding? The mass of iron 3 oxide in grams. This is one of those questions that's sort of written backwards, and so it can be helpful to explicitly think about what are we trying to find, because some of us might try to calculate what we were given. We might get our numbers switched around. We've seen it happen. Okay, so we are starting with 58.7 grams of iron. We'll just write Fe. We are also given that the mass percent equals 69.94%. So if we do our equation approach, mass percent equals grams of the part. In this case, that's iron, because this is the mass percent of iron. So that's what goes on the top. And then the iron oxide would go on the bottom, and we'd multiply by 100%. So we have mass percent. We also have the grams of iron, and we need to find the grams of iron 3 oxide. Doing a little bit of algebra, we can swap our mass percent and our grams of iron 3 oxide, our Fe2O3. Okay, so we get the thing we're looking for. Grams of iron 3 oxide, Fe2O3, equals grams of iron over mass percent times 100%. So we'll plug in the 58.7 grams. We'll plug in the 69.94%. We'll plug in the 100%. So 58.7 divided by 69.94, multiply by 100. We get a value of 83.9 grams. of our iron 3 oxide. Is this a reasonable number? Yes, it's a reasonable number. It's a reasonable number because this is the entire compound. We had 58.7 grams of iron. We would expect that the entire compound would weigh more than the part, the 58.7. We got a bigger number. That's a good sign. That's what we expect. So this seems fairly reasonable. It's also not like drastically larger. Any questions about that example? Again, I think that doing this, write out the whole formula, memorize the formula, write out the formula, figure out what it is we're looking for, plug in the rest, do a little bit of algebra. I think that's the most surefire way for most of us for getting it. The really fast way of doing it is 58.7 grams divided by the fraction form or the decimal form of 69.94%. It gets you to the same results. You're just kind of skipping some steps. So if your brain can like just do that, awesome, go for it. Just don't mess it up. All right, we can also get conversion factors from chemical formulas. So our chemical formulas contain some relationships between the number of atoms and molecules. So how many atoms of a particular element are in a molecule? For example, for this chemical formula, this is the freon that we saw in a previous example. We can get a couple of conversion factors. There's more than two, but two of the possible ones are that we get 2 moles of carbon, because we've got a a subscript of 2 on our carbon. So there's 2 carbons for every one of the whole compound. And we can expand that up to the mole scale, which is usually convenient. So 2 moles of carbon will come out if we broke down 1 mole of this compound, if we were to hit it with a hammer and break it into its component parts, or more likely burn it or hit it with electricity or something like that. If we did the same thing, but we cared about chlorine, our subscript for chlorine is 4. So if we were to break this into all of its little pieces, if we think of it like a little Lego construction, if we were to pull all the pieces apart, we'd find that we've got 4 chlorine atoms in there. So we'd get 4 moles of chlorine out for 1 mole of whatever the big thing is. And it's important to remember that these chemical formulas give our relationship between amounts in moles or atoms or molecules, not in terms of their mass in grams. I missed a letter there. Subscripts. Formulas are in units of either singular, atoms, or molecules, or moles, which is like our dozen, our very vastly large number of the singular units. So if we are working with things in grams, as we often are, because we can measure grams on a scale, like in our balance room, we'll often have to do some conversions. So we want to, in this question, determine the mass of oxygen, find the mass of oxygen in a 7.2 gram sample of this compound, aluminum sulfate. So we're starting with grams Al2 SO4 3, and we're trying to get to grams of oxygen, O. What can we get to from grams of the whole thing, Al2SO4 3? Yeah, we can do grams to moles. So we can get to moles of Al2SO43. What do we need to do that? Molar mass. So we'll have to calculate a molar mass. Can we get from moles of Al2SO43 to grams of oxygen directly, one step? We cannot. We can go from moles of the whole thing, though, to the moles of oxygen. Using the ratio or the subscripts. So based on how many oxygens there are in one of this Al2SO43. And then from moles of oxygen, we can get to grams of oxygen using molar mass. So for our molar mass for Al2SO43, we need to calculate a molar mass. We've got aluminum. We've got two of those. They're 26.98 grams per mole each. Sulfur, we've got how many? Yeah, 3. Because we've got the 3 outside of the parentheses for sulfate. So 3 sulfate groups with 1 sulfur each. And these are 32.06 grams per mole each. And then oxygen, we have how many? 12. We've got 3 times 4, 12 oxygens at right around 16 grams per mole each. And we'll sum that. And we get 342.128 grams per mole. So that's our first conversion factor. For our second step, we need our ratio or our subscript. How many oxygens do we have in one aluminum sulfate? 12. So if we were to hit it with our little atom smashing hammer, or molecule smashing hammer, for every 1 Al2SO43, we would get out 12 oxygens. So that's going to be our next conversion factor. And then for the last step, it's just the molar mass of oxygen, which is 15, almost 16. Okay, so I'm going to shrink this calculation. And starting with our 7.2 grams, the chemical is aluminum sulfate. We need to divide by our molar mass. So the grams are on the bottom, the moles will be on the top. Grams cancel. Leftover units at this step, moles, aluminum sulfate, which is right where we want to be according to our solution map. Then we can convert our chemical unit. So we can convert from aluminum sulfate to oxygen. We have aluminum sulfate on the top, so we need to put the 1 aluminum sulfate part on the bottom. Another way we can think of this is that we're getting 12 oxygens out for every 1 aluminum sulfate that we put into our little molecule or our formula unit smashing machine. So that converts our chemical. Now we just converted our chemical, so we should convert our other unit, or our other type of unit, our moles. So we're going to use our molar mass. The 15.999 goes up on the top so that the moles cancel. Grams over moles. Moles cancel. The units that we have left are go. Grams of oxygen. Questions? So do 7.2 divided by that 342 and change times 12 times 15.999, and we get 4.0, after we round, grams of oxygen. If you wanted to, you could have also used mass percent in here. So you could have calculated the mass percent of oxygen in aluminum sulfate and then use that to convert grams to grams. Questions? All right, we can also determine chemical formulas from experimental data, and this is where we get empirical formulas. So we talked about empirical formulas briefly. I mentioned that they're experimental formulas because this is what we would get if we did an experiment and we figured out what the formula was. So we can determine that from elemental analysis. So either decomposing parts of an element or combining parts of two different elements together. So we would have to be able to calculate or measure the mass of the elements when they're decomposed, when our compound is decomposed. Or we would have to figure out how much reacted together to form a certain amount of the compound. Our empirical formula represents a ratio of the atoms or of the moles of atoms, not a ratio of the masses. So this is how many of each of the individual pieces went together. So for example, like Fe2O3, what we're figuring out with our empirical formulas, we're figuring out the subscripts of the elements that are going together. You would need to know already what the elements that you're putting together or you're decomposing are. So we need moles to calculate an empirical formula. And we've got steps. So if you're wondering, hey, is there a big long list of steps that I can memorize to do this instead? Yes, but it's not that long. But there is some fun math. And by fun math, I mean math that you won't like. But it is fun for me. I think it's cool. Okay, finding an empirical formula, slide 1 of 2. You want to write down the masses. Mass of each element. If you're starting with percentages, sometimes you'll be starting with percentages, then you can convert the percentages to grams. You can just take the percent sign and swap it out for grams instead. The assumption that we're making when we do that is that we've got 100 grams of the compound. You don't need to know that that's how we're doing that. You can just remember, hey, we turn percent into grams, and that's good enough. If you wanted to multiply by something other than 100 grams to make your life more difficult, you're also welcome to do that, but 100 grams is the easy way. Okay, so once we've got our masses, the subscripts in our chemical formula are the number of atoms, or the number of moles of atoms, and so we need to convert mass to moles. So we do a mass to moles for each element. So if we've got 2 elements, 3 elements, 4 elements, we're going to be doing a bunch of converting mass to moles. I usually do this all in one step, so I'll line them up top to bottom. We'll do them all through in one step. We'll see that happen shortly. And then we divide the moles of each element. So every single one of them, we're going to divide all of them by whatever our smallest number of moles. And what this is going to do for us is it's going to turn our smallest number of moles into 1. And it'll turn everything else, because they're bigger numbers, into numbers that are bigger than 1. Strictly speaking, you can divide by whichever one you want as long as you're dividing all of them by the same thing. This will give you the nicest numbers, because typically we like to see numbers that are 1 or bigger. If you use the biggest number, you'll get 1 as your biggest number, and then you'll get a bunch of fractions, and then you get to do extra math. And then depending on your circumstances, you might be able to get away with rounding things that are about 0.2 off from a whole number, just to the nearest number. If you have subscripts that are not whole numbers, this is the fun part, then you get to multiply all the subscripts, every single one of them, including the 1, by a small whole number to get whole number subscripts. So we're going to multiply all of our numbers to get approximately whole numbers. If you're doing this on an exam, it's usually going to work out pretty nicely. There will be like a pretty clear answer. If you're doing this experimentally, especially if you had a little bit of error in your process, you might end up getting things that are not nice and tidy and neat. And so that can end up being a little bit gross. So this is a couple of the options of fractional subscripts that you might end up with, and what you would multiply to get rid of them. Typically, we don't want to be multiplying by things that are like 10 or higher, because those ratios just are unlikely. It's usually going to be small numbers. So if it ends in 0.2, 0.2 times 5 turns that into a 1. So like if we had 4.20 for our fractional subscript, we multiply by 5, that'll turn it into 21. If you have something that ends in a 0.25, you'd multiply that by a 4. That gets the 0.25 to turn into the whole number. And you kind of just pick whichever one of these is closest. Or if there's like one that's more reasonable, like it's smaller numbers, you might just pick that one. There's a whole lot of, you just kind of have to have a good sense of what's reasonable. So that's fun, because you don't have a sense of really what's reasonable yet. Any questions about the empirical formula steps? Again, usually if you're given a problem and it's not like your own lab data, it's usually going to work out pretty nicely. Okay, so let's go through these steps for a compound. So first thing we want to do, we want to get the masses of each of our compounds. So our problem says a sample of a compound is decomposed in the lab. It produces 165 grams of carbon. 165 grams of carbon. It also produces 27.8 grams of hydrogen. So 27.8 grams of hydrogen and 220.2 grams of oxygen. And we want to calculate the empirical formula. The formula has subscripts. Those are not based on mass. They're a number of atoms or moles of atoms. So we can't just go directly from grams to an empirical formula. We have to get to numbers of atoms because our atoms are different sizes. So our second step, I think, in the process, we need to convert our grams to moles. So we're going to do that by dividing by the molar masses. That looks something like this. It certainly helps if you have them memorized, but you don't have to have the molar masses memorized because you'll have them on a periodic table. Okay, and then calculator drill. We're plugging numbers in. One thing that's nice about empirical formula problems is we don't have to worry about significant figures because our subscripts are always going to be whole numbers. So we're just going to round everything at the end to the nearest whole number. However, that also means that we need to write out all of the numbers along the way because we're dealing with possibly some fractions, some 0.25 versus 0.20 comparisons. If we round early, you might end up with the wrong end result because of how tight the margins are for some of these fractions. Okay, so back to writing numbers. This is our moles of carbon. This is our moles of hydrogen. And this is our moles of oxygen. Okay, so in our sample that we decomposed, this is how many moles of each of the constituent elements we had. Good to know. But we want to know what's the ratio of all of the elements to each other. That's what our empirical formula tells us. What's the ratio of the elements to each other? And a ratio is just another word for dividing, or it brings along with it the idea of dividing. So we're going to divide all these numbers by our smallest number. So our moles of carbon is our smallest number, 13.73 instead of 13.76. So we're going to divide all of these by that entire number. With the moles of carbon at every single step. We're having a good time writing numbers. Okay, the nice thing is one of these is free. The top one, we're dividing the top thing, we're just dividing it by itself, so that one's absolutely free. 1, and the units, the moles cancel. Moles carbon, moles carbon. What this tells us is very profound. We have 1 carbon for every carbon. Very profound. Very cool. I'm joking, it's not profound, it's just, I think it's funny. The rest of these we get to put into our calculator. And this is where it's really nice if you've got the TI-36 or you got another calculator where you can click up and you can highlight the number, press enter. It pulls that whole number out and saves you a bunch of time typing numbers in. Okay, so for this middle one, we get 2.0076163 hydrogens for every carbon. So for every carbon that we've got about 2 hydrogens. And for our bottom one, our oxygens, 1.001889209 oxygens for every 1 carbon. Now we have to ask ourselves, are these numbers close enough to whole numbers that we can just round them? Yes, definitely, absolutely, 100%. Round them. So all these numbers we're going to round. So 2, we've got 2 zeros after it. We'll round that to 2. The 1.001 got a couple of zeros. That's basically 1. So it's going to be 1, 2, 1. So 1 carbon, 2 hydrogens, 1 oxygen. And these become our subscripts for our formula. So CH2O. That's our empirical formula. Questions? All right, one for you to try. Ibuprofen has the following mass percent composition. What is the empirical formula of ibuprofen? I'll give you some time to work on it. In case you forgot the trick, turn percent into grams, and then the problem proceeds somewhat like normal. So I'm going to be writing in some of that stuff while the video is paused. All right, poof. First couple of steps. So we convert percent to grams. We line up the grams of each of our things that we've got, each of our individual elements. We have to convert from grams to moles, since our chemical formula that we're coming up with in the end is going to be the ratio of the actual number of atoms of these, and they have different masses for each of the atoms, and so we have to convert to moles. So we can convert to moles. I'm using this ... to say there's more decimal places, and I'm using them. You can also do this. You just have to actually use them. If you end up with a rounding error because you forgot to put in the other things that were after that, you'll lose points if it's like a short answer on an exam or something. So there's more things, and I'm using them. I just didn't want to write them out. You're more than welcome to do this. And then we're going to take all of these numbers, each of these numbers, and we're going to divide them by the smallest one. And this is going to tell us the ratio of each of these things relative to oxygen. So we take each of these, divide by the moles of oxygen. This bottom one we get for free. We don't even have to put it into our calculator. There's 1 oxygen for every oxygen. Wow. We do a big surprise face. And then we get the numbers for the other ones that we do put into our calculator. We've got 6.5 and some change, just a small amount of change. Carbons for every oxygen that we have. And we've got about 9 hydrogens for every oxygen that we have. So we can round this 6.5 with 2 zeros and then some other stuff after it, very close to 6.5. To get rid of the 0.5, what would we multiply by? 2. We multiply by 2 because 0.5 times 2 is 1. That gets us to a whole number. We also have to multiply all the rest of these. The reason that we have to multiply, we can't have 6.5 atoms of carbon in a formula. You can't have a 0.5 for a subscript. So we have to get these all to whole numbers. We have to multiply all of them because it's a ratio. So this ends up being 13 carbons, 18 hydrogens, and 2 oxygens. And so those become our subscripts. So our chemical formulae is C13H18O2. Questions? Great. We can also, from an empirical formula, find a molecular formula. There's some extra information that we need to be able to do this. So our molecular formula, the actual number of atoms of each element in a molecule or in a formula unit, not a formula unit, is a multiple of our empirical formula. So 2 times, 3 times, 4 times, etc. It's also, though, sometimes just 1. So sometimes just the same thing. In order to determine the molecular formula, we need to know the empirical formula and the extra piece of information, the molar mass of the compound. This would be provided to you if it was on an exam or in a lab. The way that we figure out the molecular formula is that we take the empirical formula and we multiply it by some integer, 1, 2, 3, 4, 5, 6, 7, 8, etc., counting numbers, positive integer. And that number we find by taking the molar mass and dividing it by the empirical formula molar mass. So basically what we're asking is, how many empirical formulas fit into the molar mass? Or equals 1 molecular formula. That's sort of all that we're doing. So then we would have to calculate an empirical formula molar mass and do this math. How many units of empirical formula does it take to get the whole formula? Okay, so a compound has the empirical formula CH, empirical formula CH, and a molar mass of 78.11 grams per mole. We want to know what's the molecular formula. We need to figure out how many times does CH, which is our simplest ratio of our elements, how many times does that fit into 78.11 grams per mole? So we have to figure out what's the empirical formula molar mass. It's 13.019 grams per mole. And then we're going to find that magical number n, the number of times that our empirical formula goes into our molecular formula, by taking our molar mass and dividing by our newly found empirical formula molar mass. This will always end up giving you a whole number, or something's wrong. So this says 5.999692757. So we round it to 6. And then we take our empirical formula, we multiply all the subscripts by 6. So C6, H6. Benzene, probably. So that would be our molecular formula. Questions? Cool. Another way that we can do analysis is with combustion, so burning stuff. So a common technique for analyzing compounds is to burn a known mass of the compound and then weigh the amounts of the products that are made. This is useful for organic compounds, things that are based on carbon, that also typically have hydrogen and oxygen. If we know the mass of the product and the composition of the constituent elements in the product, like we know that it's carbon and hydrogen or it's carbon, hydrogen, and oxygen, then we can figure out the original amount of the starting elements. This is based on a couple of key points. All of the original carbon forms CO2, carbon dioxide. So all the carbon that was in our original compound, assuming that we burned it completely, all the carbon is only going to form CO2. All of the original hydrogen is only going to form H2O. This would be as a gas, so you'd have to capture it and collect it. And then the original mass of the oxygen, if there's any oxygen in there, is found by subtracting the original masses from the starting mass. So we would take compound mass minus mass carbon minus mass hydrogen to get the mass of oxygen. If you've taken Chem 20, you should have hopefully learned combustion. CO2 and H2O are likely products, are typical products for combustion of hydrocarbons and things that are hydrocarbons but also have oxygen. These are our combustion products. This is why you shouldn't burn stuff inside. One of the reasons you shouldn't burn stuff inside if it's not a ventilated space, because that CO2 will build up. And if you don't have complete and perfect combustion, you could also get carbon monoxide, and that's even worse. Okay, so that's cheese. Once the masses of all the constituent elements have been determined, then the empirical formula could be found. So this is one example of a setup that you might use. You've got a furnace with your sample in there, you're pumping oxygen and you're heating it up. So it burns, and there's an H2O absorber that you would have the mass. You could then get the mass of the H2O absorber once it's done absorbing stuff. You'd have a CO2 absorber, same sort of deal. That's going to absorb only CO2, and then any other stuff is going to just pass through. Then you can find the mass of the H2O and the CO2. I don't think we're going to do this in any of our labs, but it could show up as a problem. So let's do a problem. I think there's two here. So on combustion, a compound containing only carbon and hydrogen. Nice, easy. Only carbon and hydrogen produced 1.6 grams of carbon dioxide and 0.819 grams water. Find the empirical formula of the compound. So we've got 1.60 grams CO2. We've got 0.819 grams H2O. All of our original carbon went into this CO2. All of our original hydrogen went into this H2O. So if we can figure out how much carbon we've got in this CO2, if we can figure out how much hydrogen we've got in this H2O, then we can figure out how much we started with. And we can do that because we know the formula of the CO2, we know the formula of the H2O. So we're going to convert to moles, as we often do. We'll need the molar mass of CO2, which is 44.009. grams per mole. So this is the moles of CO2. That's the moles of CO2 that we have. How many moles of carbon would we have started with? Well, in a CO2, what's our subscript on carbon? It's 1, so we would have started with the same number of moles of carbon. So we're figuring out the original amount of carbon that we had. So we would have started, or we would have burned, this amount of moles of carbon. We can do the same thing for our H2O. So we'll divide by our molar mass of water. We get this many moles of H2O. So how many moles of hydrogen would we have started with? Well, we need to know how many hydrogens we have in water. How many hydrogens we have in water? 2. We've got 2 H's for every one H2O. And so this is going to tell us how much hydrogen we started with before we burned the thing, assuming that we caught everything. So we multiply by 2, 0.0909 and some change moles of hydrogen. So we've got moles of carbon, we've got moles of hydrogen. We need an empirical formula, so we need to know what's our ratio of these two things. Ratio, hopefully reminiscent of division. So we've basically gotten a weird start to our empirical formula calculation. We're like one step in to our empirical formula calculation. So we divide both of these by our smaller number, that's our moles of carbon. And we run out of space, like I love to do. We get a 2.5 and a very small amount of change. Hydrogens for every carbon. Can we have 2.5 hydrogens? We cannot have 2.5 hydrogens. So we need to do what? Multiply by 2. So we get 5 hydrogens. So CH5. Does that seem right? What did we not do? We did not multiply the other one. C2H5. And that's more reasonable. Questions? All right, we're having so much fun. Let's also do one with oxygen in it. And then I guess we'll be done after this, so we won't start chapter 4. Upon combustion, so after burning, a this many gram sample that contains only carbon, hydrogen, and oxygen produces this many grams of CO2, this many grams of H2O. We want to find the empirical formula of the compound. So we're going to be doing the same steps that we did before, figuring out how much carbon do we start start with? How much hydrogen did we start with? But we're also doing one extra step because we also had oxygen in there. But we can't differentiate, did our oxygen come from the air or our oxygen source, or did it come from our product or our thing that we were burning? So we have to do some subtraction to sleuth it out. So starting with grams of CO2, we can convert this to moles of CO2. So we divide by our molar mass. We get this number, moles CO2. And we've got one carbon in every one CO2. So our original amount of carbon was this many moles of carbon. Same steps that we did on the previous problem. For hydrogen, we started with we start with our grams of water. We'll divide by our molar mass of water to figure out how many moles of water did we make. We made this many moles of water. If we made this many moles of water, we must have had twice as many hydrogens to put in to the H2O, since there's a subscript of 2 on our hydrogen. So we multiply by 2, 2H for every 1 H2O. We must have started with, or had in our original sample, this many moles of hydrogen. Okay, so now we've got our moles of carbon, we've got our moles of hydrogen, but we don't know how many moles of oxygen we have. So we're going to use both of these numbers. We've got the moles of hydrogen, the moles of carbon. We can figure out how many grams of each of these we would have had. So for carbon, if we multiply by the molar mass, we would have had in our original sample 0.4367 ... grams of carbon in our original sample. We can do the same thing for our hydrogen. Let's figure out how many grams of hydrogen we had. It's 0.0733 ... grams of hydrogen. So we've got about 0.43 grams of carbon, about 0.07 grams of hydrogen, and we started with about 0.8 grams. So whatever isn't hydrogen or carbon in our original sample, in our original 0.8 grams, must then be our oxygen. We all tracking with that? Okay, so 0.8009 grams. Remember, this is carbon, hydrogen, and oxygen. We don't know how many of each. We just know that those three things are in there. If we subtract the grams of carbon, whatever we get out will no longer have the carbon included in it. If we also subtract our grams of hydrogen, then it'll no longer have the hydrogen, and all that's left would be the grams of oxygen. we've got 0.2908 and change grams of oxygen. And now we can do the empirical formula process that we've done before. Figure out how many moles of oxygen we have, or had to start. You be quiet. So 0.0181 and some change moles of oxygen. Okay, so now we're past, if we're thinking of our empirical formula calculation part, we're past the grams, we're to the mole part. So this is like second step of our empirical formula process. We're going to divide all of these by the smallest one. In this case, that's our oxygen. Okay, so we get our profound result, 1 oxygen for every oxygen. And we'll have to put these other ones in. Next. Okay, there's that number, divide by that number. This one's 2 carbons for every 1 oxygen. Go find that other number. This is 4 and some change, but it's close enough. We know we're going to round it. Hydrogens for every oxygen. Since these are all whole numbers, or close enough that we could round them to whole numbers, we can just put them in as our subscripts. So C2H4O. A relatively long process. Lots of steps. Any questions at all about any of the Chapter 3 material? Great, we'll stop there.